Hello, everyone. Thank you for joining our course on error correction for quantum networks. I'm Narayanan Rengaswamy. I'm an assistant professor in the Department of Electrical and Computer Engineering at the University of Arizona. So I'll be co-presenting this course with my students, Michele Pacenti and Sijie Cheng. So we will each take turns. So the course is divided into three parts. The first part, which Michele will start, we'll talk about classical error correction, kind of the essential ideas of classical error correction. Then maybe we'll take a short break, and then I'll tell you more about how quantum error correction works and how it's different and similar to classical error correction. And then in the final part, Sijie will tell you about how to use quantum error correction to make a reliable quantum network. So if you have any questions throughout the course, you can post it in the Q&A and one of us will answer there. If it needs to be answered in more detail, we'll answer it live. Otherwise, we'll answer it in text. So with that, let's get into the course. Michele, you can take it away.
Okay, thank you. I'll start sharing the screen. Okay. Can you see my screen right now?
Yes.
All right. Thank you, Professor. So hi everyone, I'm Michele. So I will take care of the first part. Maybe let me hide this. Okay. So I will take care of the first part on classical error correction. And I will start right away by showing you this sentence. Obviously, there are some errors in it, but I guess most of you are able to get back to the meaning of it, which is a quote from Richard Hamming. This is possible because so you guys were able to get back the original meaning because we actually apply error correction on a daily basis in our lives, because human language can be interpreted as a form of error correction. So indeed, we can define S to be the set of all the human sounds that we can produce, or equivalently, we can take S to be all the possible combinations of letters and symbols in our alphabet. And then we can define L to be a subset of it, which is our language, which is actually the set of all the possible words, say, of the English language. And all the other combinations of letters and symbols belong to S minus L, so don't belong to the language. And we can get back the meaning. Actually, we can correct errors in sentences, because we can map back what's here back in the set L by doing what we call maximum likelihood decoding, which is actually bringing back the erroneous sequence to a word belonging to the language. And so, for instance, the word actually this sequence here maps back to typing, or this sequence here maps back to thinking. Now, obviously, in the human language, we have correlation between words. So also, because of the context, we can say that this is thinking and not thanking. We will assume to the rest of the lecture that words are independent, because this is actually what happens in error correction when we talk about block codes. So error correction is the equivalent of this, of the language, but for machines. So we know that machines use the binary alphabet. So we will consider the field of binary sequences of length n. That these are the two tables for additions and multiplication in the binary field. And as I just said, we will consider each word to be independent. So we will consider block codes. So we can repeat actually what we just did for the human language. We take the set of all the possible binary vectors of length n, which contains 2 to the n elements, obviously. And then we can take a subset of it, represented by the blue dots. and say that those sequences belong to our code. And then automatically all the sequences outside our code will belong to, if you recall, the set S minus L. So this is actually a way to define a code simply by describing a list of all the possible elements belonging to the code, which are called code words. Let's introduce an example that we will carry on for the whole presentation, which is actually a very simple form of error correction, which is called repetition code, and is something that even in the analogy of human communication exists. When you want to clarify something, you just repeat the word, right? The concept that you want to transmit. And so this is actually what happens in the 313 repetition code. Sorry, my cat is pushing the door, but hopefully it will stop soon. So the 313 repetition code is the most simple form of error correction. When you just take one bit, that can be either 0 or 1, and you just repeat it in this case for 3 times. But first of all, let's introduce the notation that we use here, which is denoted with the nkd term. So n is called the code length, and is the number of bits in the code word. K is called the code dimension. So K is the length of the information sequence that we encode. In this case is 1. And the code has in general 2 to the K code words. And 3 is called the minimum Hamming distance. Hamming, of course, is the same Richard Hamming from the quote of before. And in this code, we have 2 code words, right? 2 to the K. K is equal to 1. So the all 0 code word and the all 1 code word. As you can see, the bit 0 is repeated 3 times. And the bit 1 is repeated similarly 3 times. And we define the Hamming distance to be the number of positions in which 2 binary vectors differ. So for instance, the distance between these two code words is 3, because on all the 3 positions, we have a different entry. The parameter d in the code, the minimum distance of the code, is the minimum among all the distances of all the code words of the code. And in this case, we only have 2 code words, so the distance is only 1, and it's 3, and it coincides with the minimum distance. Now, the concept of minimum distance actually is directly related to the correction capability of the code. So, for instance, we can reorganize the space of all the binary sequences of length n, actually of length 3 in this case, by taking the 2 code words and reorganizing all the elements that don't belong to the code into what we call Hamming spheres, basing on their distance with the code words. So for instance, the sequence 001, sorry about that. So the distance 001 is at distance 1 with the all 0 code word. And the distance the sequence, for instance, 110 is at distance 1 with the all 1 code word, but at distance 2 with the all 0 code word. And so we actually reorganize the space using these distances. And in this case, we define the parameter t, the number of correctable errors, to be half of the minimum distance. This bracket that you see here is the floor function, which essentially is the smallest integer nearby, the smallest integer of the nearby the argument. Okay, and so we will see in a minute why this parameter t is important and how Hamming spheres can be used to perform the maximum likelihood decoding, just like we did in our example with the human language. But first, let me introduce the notion of code rate, which is defined as k over n. Essentially, it defines the amount of redundancy that we use to protect our information. So if n is slightly bigger than k, then the rate will be close to 1, and we will have a high rate code. So we don't use a lot of redundancy. If n is much larger than k, then the rate will be close to 0, and we use a lot of redundancy to protect our information. Obviously, generally using more redundancy helps in correcting more errors, and that's why especially in quantum, we are more focused on very low rate codes. Okay, so let's get started with the first poll question. So assume that you have 155, 10, 21 code. How many redundancy bits are used? So how many bits are not information bits in a code word? How many errors are guaranteed to be corrected by the code? And how many code words does the code have? Excellent. So while you answer the question, I will take out the cat. All right, so most of you answered correctly. So indeed, the number of redundancy bits is n minus k, because we have 10 information bits. So 155 minus 10. We can correct 10 errors because t is equal to half of the minimum distance. So 21 minus 1 is equal to 20, divided by 2 is 10. And we have 2 to the k, so 2 to the 10 code words. Okay, let's move on. Of course, when we talk about error correction, we must introduce the error model, which usually is described as a channel. So a channel is a theoretical framework that describes, actually tries to model the underlying physical scenario where the errors occur. A very
Michele?
simple.
Sorry, just to pause. So there was a question about the meaning of D in the Q&A. So I answered it there, but maybe just to be clear, could you repeat the definition of minimum distance just for everyone?
Absolutely. So the minimum distance is defined, and so the Hamming distance between words is the number of positions in which they differ. Now, when you have a code, you have many code words, and you, of course, each code word will have some minimum distance, actually some Hamming distance with all the others. So among all the distances between each code word, the minimum distance is the minimum among them. And we take into account the minimum because it gives us the guaranteed correction capability of the code, because by this formula, the minimum distance is related to the number of correctable errors. So the minimum distance gives us a measure of how many errors the code can correct, essentially. That's why we consider the minimum among them. But generally, you can define a spectrum of distances where actually, obviously, the minimum of those matters the most. And actually, hopefully, it will be a little bit clear later in a little bit more clear in the example, the work, how the minimum distance works. We will see it just in a moment. But as I said, I need to introduce an error model. So we will consider the binary symmetric channel in this case. Is sufficient for our scopes, where each bit 0, 1 has a probability of being flipped alpha, and a probability of not being flipped 1 minus alpha. So obviously, the most likely error is the one that involves only 1 bit. So assuming that we transmit 3 zeros, the probability of having just 1 error is alpha times 1 minus alpha squared, which is the probability of not having a flip in 2 bits, while the least likely error is having a flip over the 3 of them. So taking into account this error model, let's see an example of how the maximum likelihood decoding is performed and how the hemisphere concept works actually. So assume that we have a code word X that we transmit through a channel, and the binary symmetric channel introduces 1 error in the central bit. The maximum likelihood decoding will give as output x hat 0, 0, 0. Simply because 0, 1, 0 belongs to the hemisphere of 0, 0, 0, right? And it's like this because 0, 1, 0 is at distance 1 with 0, 0, 0, and at distance 2 with 1, 1, 1. So the most likely code word is the one at minimum distance with y. So between the two, obviously, the 0 code word is the most likely transmitted code word. But of course, we can also have a decoding failure. And this is actually the topic of the next poll question. So assume that we still transmit 0, 0, 0, but now the channel introduces two errors. So that we receive 1, 1, 0. What is the output of the maximum likelihood decoder? I guess this concept of hemispheres and decoding is pretty much clear seeing the results. So 82% of you answered actually correctly. So the most likely transmitted code word given this received sequence is the L1 code word, simply because 110 belongs to the hemisphere of 111 and is only at distance 1 with 111 and at distance 2 with 000. So in this case, when the channel introduces two errors, what happens is that our decoder introduces one more error. Thus, using error correction in this case is worse than not applying error correction. And this is something that we cannot do anything about, rather than using a code with a higher minimum distance. So for instance, repeating a bit 5 times instead of 3 times would let us correct even with 2 errors. So there's a raised hand. If you guys could help me with that. Narayanan and Sijie, maybe there's some question.
Yeah, please type your question in the Q&A. I will answer it. Thanks.
Okay, sounds good. Just feel free to interrupt me when the answer shows up. So let me formalize a little bit the maximum likelihood decoder. So here, again, we can see our space, the space of all the binary sequences of length n. The orange dots are code words, and we see regions that actually pack the space into our hemispheres. Actually, if actually they don't look like spheres now, but we can equivalently define them as decision regions or Voronoi regions. And if I receive the vector y, which is a white dot, falls in some specific region, it will be mapped back to the orange dot of that region. And if an error brings a code word to the region belonging to another code word, we will have a decoding failure. And now we will just prove that in the case of binary symmetric channel, minimum distance decoding is equivalent to maximum likelihood decoding. So let's define D to be the Hamming distance between two binary sequences X and Y. We have the conditional probability of a received sequence Y given a code word X to be essentially the probability that the binary symmetric channel introduces D errors, right? So first, for instance, assume that X is the O0 code word, and I receive a binary vector with D once. Then it means that the binary symmetric channel introduced the errors, and this is the probability like we saw before when I talked about the binary symmetric channel. The maximum likelihood decoding rule is essentially tells us that the most likely code word X hat is the code word X that maximizes the posterior probability P of X given Y. Now we can use Bayes' rule to write this term in this way. Assuming that each code word is equally likely, P of X becomes constant, P of Y doesn't depend on X, so this is equivalent to maximizing P of Y given X, so picking X that maximizes this. Since we have some exponent here, it's convenient to consider the logarithm of this quantity and use some simple logarithmic rules. Then we reorganize the formula in this way. This term doesn't depend on x, so we can get rid of it. This term, we have a d that depend on x, while log 2 of alpha over 1 minus alpha is negative. So to maximize this quantity, we have to minimize this negative term. So we have to minimize d. So this means that for maximizing, so the code word x that maximizes this property is the one that minimizes the minimum distance with the received vector y, as we intuitively saw in the previous example. So minimum distance decoding is equivalent to maximum likelihood decoding. Okay, are there any questions? Otherwise, I would move on to the next topic. Okay. So as I said, to define a code, you could simply list all the code words, but this is not an efficient representation, obviously, because a code has 2 to the k code words. So if k increases, the number of code words grows exponentially. So we can represent a code using a more convenient representation, actually matrix representation. And indeed, the code is uniquely defined by specifying 2 matrices, the generator matrix and the parity-check matrix. So the generator matrix is that matrix G, so it's a binary matrix G, such that picking a binary vector of length k and multiplying it by G, we always get a code word. On the other hand, the parity-check matrix of a code is a binary matrix, such that if we multiply a code word for H transposed, we get the all zero vector. And vice versa, right? So if we have a binary sequence and we multiply it by H transpose, we get 0, then X is a code word. So these are 2 equivalent representations for a code. And indeed, a code word belongs to the image of G. So G, the generator matrix, generates the code space. And equivalently, the code space is the kernel of the parity-check matrix. And because of this, obviously, this property holds. So let's take a look at the matrices for the 313 repetition code. So obviously, U is either 0 or 1 because k is equal to 1. So it's only 1 bit of information, as we saw. G is that matrix that generates the code space. So those 2 code words. And it's easy to see that it looks like this. So the generator matrix has k rows and n columns. And similarly, one can see that the parity-check matrix will look like this. And it has n minus k rows and n columns. And we can convince ourselves that this is indeed the parity-check matrix of the repetition code by multiplying the all one code words by H transpose. This means that we take the binary sum of all the columns, which is the all zero vector. What happens if we multiply something that is not a code word for H transposed? We get what is called syndrome.
Michele, just to pause, maybe just for clarity, could you repeat the previous 2 slides? I think maybe we can go a little slower so that everyone catches the idea.
Absolutely. So
Thanks.
essentially, we can define our code using 2 matrices, the generator matrix and the parity-check matrix. These are 2 binary matrices. In G, essentially, each row is a binary vector and is a code word. And G is essentially the set of code words that generate the full code space. So each code word is a linear combination of rows of G. On the other hand, another equivalent representation for a code is the parity-check matrix, and is a binary matrix such that when you multiply a code word for the transpose of it, you always get the all zero vector. these two matrices, and actually the code, because of these properties, we say that the code belongs to the image of the generator matrix as well as at the kernel of the parity check matrix. And because of that, this property holds, right? G times H transpose is equal to 0, since G is just a matrix where each row is a code word. And this is a convenient representation because G, the dimension of G and H grow linearly with K and N. So especially the concept of parity check matrix will be important when we will talk about LDPC codes. And the parity check matrix is used to perform decoding using what we will see to be the error syndrome. So as I said, the parity check matrix is designed such that multiplication of a code word for the transpose of it always gives you the zero vector. But if you multiply a binary vector which is not a code word, in general you will have a binary vector as a result of your multiplication. That binary vector is the syndrome. So assume that we have a code word X and we transmit it over a binary symmetric channel. Then we have an error E. Then we can model as added to the code word X. So your received sequence will be X plus E. Obviously, this is a modulo 2 sum. So E will represent the flips of the bits of your code word, right? As we saw before. Now, what happens if we multiply? What happens when we multiply Y by H transposed? Y is given by X plus E. But we showed before that this term always gives 0 by definition of parity check matrix. So the syndrome is only dependent on the error that happened in the channel, actually, that the channel introduced. And turns out that we can use S, so this binary vector that we compute, to perform decoding in the following way. We will see it with an example. So assume that we transmit the 0 vector in our 313 repetition code, and we have a flip in the first bit. Then Y will be 100. We compute the syndrome, and we actually get 10. So now we can construct a table, which is called a standard array table, which is constructed in the following way. We have 2 to the k column, so 1 column for each code word. At the top of each column, we have a code word. And we have 2 to the n minus k rows. So a row for each actually parity check equation. So we have at the end of each row, we have all the possible syndromes. And the entries in the table are all actually binary vectors that we can receive. So we can use the standard array table to perform decoding in the following way. We compute the syndrome, and we locate the syndrome in the table. For instance, it's here in the second row. And then we go left until we located the received sequence Y. Then in that column, the top element will be the most likely code word. And the leftmost element will be the most likely error, which in this case coincides with the received sequence. So let's make another example. Assume that I measure, say, I compute a syndrome of 1, 1. Then I will go here. And then basing on the received sequence, for instance, say I receive 1, 0, 1. Then the most likely code word would be 1, 1, 1. And the most likely error would be 1, 0, 0, 1, 0. Another example. Let's assume to have a different code now. So we will consider the 743 Hamming code. The generator matrix and the parity check matrix will look like this. since k is equal to 4, we have 2 to the k, so 16 code words, which are these. And the standard array table will look like this. So as you can see, we slightly increased n and k, but the size of our table increased a lot. And this is the main reason why, although this is actually maximum likelihood decoding, so this is the best type of decoding that we can do, it's not scalable for large code. Say, assume to have a code of length 100 and dimension 50, then the size of the table will make infeasible any type of efficient decoding. So although this is actually the best we can do, usually we use different techniques for decoding because this is not feasible. But before moving on, let's do another poll question where you guys will try to use the standard array table to decode. So assume that you receive the sequence 110, 1110, and you measure a syndrome of 011. Then what is the most likely transmitted code word and the most likely error? So as we saw before, you locate the syndrome in the table, and then you go left in the row until you get your received sequence, and then you immediately know what are the most likely error and the most likely transmitted code word. I guess we can stop here. Okay, thank you. 66% of you answered correctly, actually. The right answer is D. So let's briefly see how we perform decoding. So we locate the syndrome here. We go left until we meet the received sequence. Then on top, we have the most likely code word. And in the leftmost position, we have the most likely error. So excellent. Okay, so before switching to LDPC codes, let's just briefly introduce the notion of dual codes. So let's assume to take the parity-check matrix of the repetition code and define it to be the generator matrix of another code. And the generator matrix of the repetition code and define it to be the parity-check matrix of another code. What we get is actually a completely different code. It's called a single parity-check code. And obviously, this property will hold. So they will be mutually orthogonal. So actually, one code will belong to the kernel of the other because of this definition. And we say that these are dual codes. So we won't focus actually on this, but it will be important in the quantum part in CSS codes. So I will just leave it here and won't go deeper on that. And let's focus now on LDPC codes. So LDPC stands for low density parity check, which are essentially codes defined to have actually a sparse parity check matrix. Sparse, which means that it has a lot of zeros and just a few ones, simply. So these codes with sparse parity check matrices, on one hand, they can be decoded very efficiently using iterative decoders. On the other hand, actually you can construct very, very good codes with sparse parity check matrices. And for good, I mean codes with very high minimum distance, so that can actually correct a lot of errors. So we will focus on decoding in this lecture. And generally decoders work on the Tanner graph of LDPC codes. So let's define a Tanner graph. A Tanner graph is defined actually from the parity check matrix of the code. So this is again the parity check matrix of our repetition code. And we define each column to be a variable node denoted with V, and each row to be a check node denoted with C. So we define V to be the set of variable nodes, C to be the set of check nodes. So each check node, as you can see, is a parity check equation, what we call a parity check equation. Just to remind, a code word is able to satisfy all the parity check equations, meaning that all the parity check equation will give 0. So each parity check equation is represented by a check node in a graph, and there is an edge between a variable node and a check node if there is a 1 in the corresponding row I and column J in the parity check matrix. So for instance, there will be an edge between B1 and C1 because here we have a 1, but there won't be any edge between B1 and C2 because we have a 0 here. So the Tanner graph of the repetition code will look like this. And it's a bipartite graph, which means that we have two sets of edges, B and C, and there are no edges between two nodes of the same type. So generally, a Tanner graph of an LDPC code will look like this. So this is actually a small code, but it's an example of an LDPC code. In particular, this is a regular code. So we define dv to be the variable node degree. The degree of a node is the number of incident edges that a node has. And you can check that in this graph, all the variable nodes have degree 3. And we denote the neighborhood, which is the set of neighboring check nodes of V using this notation n of V. And similarly, you can check that also the check degree DC is constant and is 5. And we still use this notation n of C to denote the neighborhood of this check. So this is actually a regular code, but there are also LDPC, irregular LDPC codes where degrees are just different for every node. And regular and irregular codes, they have different properties, and actually it's very interesting how they perform differently, but it's not the scope of this course. So let's pull out another question. So this also should be simple for you guys. Given the Tanner graph, what is the corresponding parity check matrix? Okay, excellent. So even this time, 62% of you answered correctly. So the answer is B. We can quickly check, for instance, that the third variable node is connected to the first and the second check node. So the third column of H is 1, 1, 0. Or similarly, the second variable node is connected to the first check node and the second and the third check node. So the second column will be 1, 0, 1, so on and so forth. But many of you actually got it right. But don't relax too much because there's immediately another poll question. So given the Tanner graph below, which one of the following statement is false? N is equal to 25 and the check degree is 5. The check degree is 3. N equal to 25 and the Tanner graph is bipartite, and it's a regular LDPC code. Should be enough. Okay, thank you. So again, the majority of you answered correctly. It shouldn't actually be hard to check that the other 3 are correct statements. So that's pretty much what we need in LDPC codes to start looking at some decoding algorithm. So the decoding algorithms usually are designed to actually have low complexity, which means that the number of operations, the number of iterations that they go through scales linearly with the length of the code and not exponentially. Iterative decoders usually actually operate on Tanner graph, and they involve an exchange of messages between variable nodes and check nodes. And that's why these algorithms are also called the message passing algorithms. And they proceed with the iterations until the stopping criterion is met, which is if they reach a valid code word estimate. or the maximum number of iterations is reached. So as an example of iterative decoder, we will look at the bit flipping algorithm, which is probably the simplest decoder that you can think of. So first of all, we have variable to check and check to variable messages. At the first iteration, which is denoted by this 0 in the bracket here. So the initialization, essentially, the messages that each variable node j sends to each check node I is essentially the received value from the channel. So the jth bit of the received sequence. The check to variable message from the check node I to the variable node j at the kth iteration is the binary summation, which we denote with this symbol, of all the incoming messages of the previous iteration in the neighborhood of the node I. And then starting from the second iteration, the variable to check message becomes like this. So there's a threshold that we define, usually to be half of the column, the variable node degree, but it can be arbitrarily defined. We take all the incoming messages from the neighborhood of the variable node j, and we sum them. If this sum is bigger than this threshold, then we take the previous message at the k minus one iteration and we flip it. If this summation is not above the threshold, we keep it the same. Okay, so hopefully the next 4 questions will help you to better understand and get the concept. So assume that we have a check node connected to these variable nodes with these values. Now, basing on the check to variable node update rule, which again performs the binary summation of the incoming messages, what is the check to variable message computed at this check node? So let's just recall that the binary summation obviously will be 1 if you have an odd number of non-zero elements, and 0 if you have an even number of non-zero elements. Again, the majority of you answered correctly. There are some that answered actually A, but maybe it wasn't clear that this is a binary summation, which means that obviously we perform the summation over actually modulo 2, and because we have 3 non-zero elements, the result of this summation is 1. And let's go with the next poll. Now we compute the variable to check message given these 3 incoming messages. So again, now we perform actually a real summation, non-binary. We compare the result of the summation with the threshold, which is 1 in this case. And if the summation is above the threshold, we flip the previous message. Otherwise, we keep it the same. And the previous message is 1. So, right. I guess it's enough time, Sijie. Thank you. So, again, the majority of you answered correctly. Indeed, since the summation of these messages, which is this term here, is 2, 0 plus 1 plus 1, is above the threshold 1. So we flip the previous message back to 0. Okay, excellent. So now we can briefly look at a decoding example using this parity check matrix that I designed for this presentation. So it's a regular code. You can see that you have, actually we have variable degree of 2 and check degree of 3, and it's regular. The Tanner graph looks like this. So assume that we receive this sequence Y here. And then obviously the initialization is that at each variable node, the received value is say loaded and transmitted to each connecting check node. So for each check, as we saw in the poll, we perform the binary sum. So for instance, the first check node is connected to this variable node, which has value 1. This variable node has value 0, and this variable node has value 1. So we have 2 1s and 1 0. So this check to variable message is 0. And similarly, you can check the others. Okay. So now we send these messages back to the variable nodes, and at each variable node, we perform the summation of the incoming messages, which will look like this. So for instance, the first variable node is connected to this check, which has value 1, and this check, which has value 1. So this is 2, and similarly the others. Now, since beta is equal to 1, we flip the variable nodes which have associated the number 2. So actually, they're involved in 2 unsatisfied parity check equations using the variable update rule. And so we flip these bits that I colored in red. And now, again, we compute in the second iteration the value at the check nodes, performing the binary summation of the messages. And then we send back the messages to the variable nodes. We have these values here. There's only this bit involved in more than one unsatisfied parity check equation, which is this one and this one. So we flip this back. If you recall, this was flipped by the decoder, and now we flip it back. And we actually have reached to a valid code word because we have the all zero syndrome. So our decoding was successful. Just
Michele,
briefly.
maybe just for clarity, could you do the example once more? And also, there is a question in the Q&A which I thought is better answered live. So what is the intuition of the bit flipping algorithm?
So excellent question. So the intuition is that in each iteration, we let's take a look at the update rules. Okay, maybe there. So the intuition is that at each iteration, we want to flip the bits that are involved in a large number of unsatisfied parity check equations. So this number here, so the summation of the incoming check to variable messages is the number of unsatisfied checks or unsatisfied parity check equation in which the bit is involved. The higher it is, and the higher is the probability that that bit is in error. So by flipping those bits iteratively, the hope is that when you compute again the check to variable message, like in this case, the weight, so the number of ones in your syndrome is reduced. So actually, this is pretty much it. It's the intuition behind the bit flipping is to flip those bits that are most likely to be in error because they're involved in many unsatisfied checks. And obviously, if one bit is not involved in any unsatisfied parity check equations, then it's likely correct. This is the rationale behind the algorithm.
Sounds good.
Okay, excellent. So just I wanted to briefly look at belief propagation. So I don't want to go deep into this, but since it's a very important algorithm, which is also used in many other fields other than error correction, I thought that it would be nice to have an idea on how it works. So it's again an iterative decoder, message passing decoder, and it's based on the probability marginalization. So the key idea is that now we want to compute maximum likelihood decoding on each bit. So we want to estimate the value of the bit j, can be either 0 or 1, such that it maximizes this posterior probability. And because of probability marginalization, we can express this as a combination of all the other probabilities of all the other bits rather than j. So you can see this is this depends on x1, xj minus 1, xj plus 1 until xn. So this is called marginalization. And the idea is to compute a bitwise maximum likelihood, but actually perform local computations. So to sort of exploit the fact that these probabilities are somehow independent from each other. And this is indeed true when we have a tree. So assume that we have a tunnel graph that looks like this. So we have 5 variable nodes and 2 check nodes, and it looks like a tree. We want to estimate the most likely value of x1. So we want to see if it's either 0 or 1. So we want to compute the value of x1, 0 or 1 that maximizes the posterior probability. Then we use marginalization to express this probability as a combination of the other the probabilities of the other bits, x2, 3, 4, and 5, that we can rewrite like this. And actually, one can show that it can be expressed like this. So we have P of y given x is the probability from the channel. Essentially, is the product of this input from the channel W, Wj, times these elements here, these functions. These functions depend on the parity check equations, and actually they are equal to 1 if the parity check equation is satisfied, and equal to 0 if it's not, meaning that the only terms that will contribute to this summation are the elements that will satisfy both the parity check equations. But now you can see that there are 2 independent terms here, so that we can write this probability as the product of 2 contributions, and these 2 contributions can be computed locally at each check node. So we take the incoming message from C1, which is this blue term here, and the incoming message from C2, which is the orange term. We multiply them together, and with W1, which is the input probability from the channel, and we get the most likely estimate of x1. And then we do this systematically for each bit. And so without going too deep into this, we have that the variable to check update rule, actually the variable to check message will be a product of the incoming check to variable messages. The check to variable messages will be a summation of the incoming messages for a variable to check messages, and the probability of each bit to be either 0 or 1 would be the product, the simple product of the incoming messages. But again, I don't want to go too deep into this. It was just to motivate the idea behind belief propagation, and obviously there are many approximations of this that are more efficient, but that's enough for this talk.
Maybe quickly you can mention why it's also called sum product.
Yeah, sum product because as you can see here, we have the only operations involved in the computation are summations and products of probabilities. So before leaving the stage to Professor Rengaswamy for the quantum part, let's just briefly, I just wanted to briefly mention how to assess the performance of a code and a decoder. Because this also gives you the means on how to look at plots when you read papers in error correction. So generally, people use Monte Carlo simulations to look at the performance of a code and a decoder over some channel, which is essentially a random sampling of errors. And we simulate the correction in the following way, actually. So we choose an error model, a code, and a decoder. We define a number of samples for the simulation, which has to be obviously large enough. And we fix the parameter of the channel, for instance, the probability of error of the binary symmetric channel. And then for each sample, we generate a code word, which can also be the O0 code word. We generate a random error. We add it to the code word, compute the syndrome, and decode. If the decoder fails, we count a failure. And when we simulated all the samples, we get the probability of error after decoding by dividing the number of failures of the decoder by the total number of samples. Obviously, we can repeat this for different error probabilities from the channel, and we plot the probability of error from the channel versus the failure rate. And the plots will look like this. So I chose this picture because it's actually shows the performance of different classes of codes. This is not the binary symmetric channel, it's AWGN channel, but the key idea is the same. So the dashed line is the error, actually. So on the y-axis, we have the error probability after decoding, and the no coding curve is the dashed line. And when we use error correction, you can see that we are below. So we get actually a smaller probability of error fixing the physical, the error probability from the channel. And you can see that particular turbo codes and LDPC codes perform actually quite well. And finally, let me make a clear distinction between the waterfall region and the error floor region. So the error floor phenomenon happens for low probability of error. So this is actually a binary symmetric channel. So you see that at a certain point, these are different decoders. At a certain point, when the probability of error is low, this slope of the simulation curve changes. And this is known as error flow phenomenon. And in general, you can always distinguish these two regions in a simulation. Okay, that was everything from my side. I'm happy to answer questions and leave the stage to Professor Rengaswamy. And thank you for your attention.
Thank you, Michele. That was a great presentation. So if you have more questions, you can put it in the chat. It was a lot of technical material, we know, but looking at your answers to the poll questions, it looks like Michele did a great job, and I think you are also able to follow. Most of you get many of the answers right. So, but because there was a lot of technical material, maybe we'll take a 5-minute break. So we'll resume in 5 minutes. But in the meantime, if you have questions, you can post it in the Q&A and we'll try to answer it as soon as possible. So we'll return in 5 minutes.
So there's a question actually on the first plot. What was the x-axis? So there was the AWGN channel, so it was signal to noise ratio, which was essentially an equivalent, if you want, definition of the probability of error. So I didn't want to get deep into it.
Yeah, so it was just a different channel. So it was a parameter related to that channel, but we didn't get into that discussion. Okay, everyone, welcome back. Can you see my slides, Michele?
Yes.
Okay, perfect. Okay, so now you all learned about the basic ideas of classical error correction. So Michele took you through what you mean by the code dimension, K. So you encode K message bits into N code bits. And so here is one way of looking at it. So if you had these so let me use the laser pointer. Yeah. So if we had, say, 1 bit of information, if it goes through errors, then it's hard to detect errors because that's an information bit. And so if information goes through errors, you cannot detect it. So what you do is you encode into a classical code, basically by adding some redundant bits. And then it's like saying united we stand, divided we fall, right? So that's the basic idea of error correction. You store information in multiple correlated elements and use these correlations to detect and correct errors. So this is the exact intuition you should have even for quantum error correction, although the mathematics works a little different. So we'll go through that in this part of the talk. So on the right side, you're seeing a different plot. So Michele showed you some error rate curves. So this is another way of plotting error rates in quantum, where people plot time to failure, which is basically 1 over the error rate that Michele was plotting. So as you can see, so this is a curve that we'll come back to later. So this is error rates for what's called the surface code, which you might have heard of. So as you increase the size of the surface code, you see that the time to failure keeps increasing. So things get better and better, but only on the left side of this point, which is called the threshold. On the right side of the point, when the physical error rate is much larger, then actually increasing the code size makes things worse and worse. But on the left side, things get better and better. So this is something that you will learn at the end of the course, but I wanted to show you so that you see what's coming. Okay, so in quantum computing or quantum networking, so we have to correct errors, just like we did for classical codes. However, there's one more important thing you need to do. So let's say you have k logical qubits. So in quantum, instead of message bits, we call them logical qubits. So here I have k logical qubits. Now you want to perform some algorithm. Let's say maybe you want to factor a 20-bit number, right? So that's a quantum algorithm, like Shor's algorithm. And then you want to end up in a new state. However, every component of the algorithm is made up of gates like this. So on the left side, H, T, and this control knot are three fundamental quantum operations. And you can compose any other quantum operation as a sequence of these three gates. So classically, for example, you know of the NOT gate, of the AND gate, XOR, and so on. So these are quantum versions. So these are quantum gates. So you compose some circuit to implement this logical operation, but it's noisy. So if something fails in the computation, then you cannot know. Which is why you take these k qubits, you encode them into n qubits, n larger than k, and then you do all operations on these n qubits, and hopefully you can do them in a fault-tolerant way so that any errors that occur can be corrected using this quantum error correcting code. And after you're done with the computation, then you can decode, and hopefully you'll end up at the same place as before. So this is the longer path that you take to get to the state you want, which means that you have to translate all of these logical operations into physical operations. So this is an integral part of quantum computing, which you don't see as much in classical error correction, because there you mainly have to decode errors. Here you have to decode errors, but also compute on the encoded information. So we'll discuss a little bit about this in this course. Okay, so let's start with the basics. So what are some of the basic quantum operations? So here are two basis states, 0 and 1. We call them ket0, K-E-T, ket0 and ket1. So that's what this vertical line and angle bracket together, that's called the Dirac notation or the ket notation. So the X gate, the quantum X gate, is basically the quantum version of the classical NOT gate, which means it flips 0 to 1, it flips 1 to 0. However, remember that this ket0 and ket1 are not bits anymore, they're qubits, which means they actually they're basically length 2 vectors, which can be represented on this imaginary sphere called the block sphere. So 0 is represented like this, 1 is represented like that, which means X is basically a flip across this x-axis from 0 to 1 or 1 to 0. The next operation is called the phase flip. This is the new thing that you get in quantum. So classically, that is just the single X flip. In the quantum case, you have the phase flip, which retains 0 as it is, but for 1, it flips the phase. So it brings an extra phase of -1 on the qubit. And this can be represented also on the block sphere. But so because it's hard to see, the phase flipping on this line, you can represent this operation using another pair of basis states, which we'll call plus and minus, which lie on the x-axis. And then you can visualize the phase flip as actually a rotation about the z-axis. Finally, there is the combined bit phase flip, which is simply a combination of the phase flip and the bit flip. Now, once you have defined these basic quantum operations, you can define the quantum version of the BSC, so which we call the depolarizing channel. which means if you input a single qubit state, which is some arbitrary linear combination of the 0 state and the 1 state, it's a superposition. Then you send it through this channel, and the channel has a parameter epsilon. Then what happens at the output is the output state is the same as the input with probability 1 minus epsilon, and with probability epsilon over 3, one of these three flip operations can occur. So as you can see, this is a natural generalization of the classical BSC. Now here is the first poll question just to warm you up. So I've told you about the X, Z, and Y operations. Now can you tell me if Y, how Y can be related to X and Z? Okay, maybe we can end here. So as you can see, most of you got the right answer, which is C. So maybe there was a little bit of confusion between choosing between C and D, but you can verify that you first have to apply Z to the state, which flips the face if it's 1, and then you apply X, and then the I always carries over. Okay, let's proceed. So these are the basic poly operations on a single qubit. Now let's go to multiple qubits. So let's say we have n qubits, in this case n equals 3, then each of those qubits can go through one of these poly operations. And mathematically, we represent that using this tensor product or the Kronecker product. So you can, so for the purposes of this course, you don't have to know too much about what the Kronecker product or tensor product is, but it's just a way of mathematically representing that these are three independent operations on three independent qubits. So for convenience in papers and even for this course, we'll sometime drop this tensor product when it's clear from the context that these operations are acting on different qubits. So, so this is basically an abusive notation. So depending on context, it could be three things on the same qubit or three different things on different qubits, but it'll be clear from the context. Okay, so now let's see what the poly group is on n qubits. So these are the poly operations. The poly group consists basically of tensor products of these polys. So you have 4 possible operations on each qubit, which means on n qubits, you have 4 power n tensor products. But then there can also be a global phase, 1 I minus 1 or minus I. For example, I times x is also a valid poly operation. So that's how you make a group. So yeah, so the group is generated by these 4 poly operations on each qubit. And the very useful property of this group is that these so if you just take the tensor products of I, X, Z, and Y, you can check that they're Hermitian, which means their conjugate transpose is themselves. So X conjugate transpose will be the same as X. And these actually form an orthogonal basis for all square matrices under this particular inner product. So this is the very useful property of poly operations, and that's why they are widely used. And this is why you can kind of decompose arbitrary operations as linear combination of poly operations. Good. Now, these poly operators have, they satisfy a single property, meaning that any pair of non-identity poly matrices anti-commute, which means what I mean is that if you take a state psi, if you first apply X, then Z, so there's no tensor product here. These are just acting on a single qubit. So if you first apply X and then Z, it's actually equivalent to doing first Z and then X with a minus sign. So XZ is basically minus ZX, and similarly for XY and YZ. So one thing you might have already noticed is that in the circuit kind of notation where I represent gates using these boxes, time goes from left to right. But when you write the mathematical action on the state, time actually goes from right to left because you first apply X, then Z. Whereas here you're starting from the state psi here on the left on both sides. So just keep that in mind for the rest of the talk. Now let's see what happens when you go to more than one qubit. So you have 2 qubits here, and you're applying XZ, XZ on each of them. And you know that for on each of them, they are minus ZX. which means you can combine these minus ones and you just get z tensor z times x tensor x. You can just go through the sequence of equalities. And the property we are using is this property of Kronecker products or tensor products. So if you have A tensor B times C tensor D, then you can first multiply the corresponding matrices on each side of the tensor and then take the tensor product. So here, for example, I'm first doing Z tensor Z and X tensor X equals, I'm multiplying this Z by this X, this Z by this X. And then I know that Zx is minus Xz, and then these minus signs cancel, so I can completely reverse the order of operations. And now we see the kind of basic example of two Pauli matrices on two qubits that actually commute. And this is how we make stabilizers which are quantum versions of parity checks, as you will see shortly. So here I'm considering a stabilizer group, which is generated by these two operators, x tensor x and z tensor z, and dropping the tensor, and you can take all possible products of this. You only get these four operators. So you get I tensor I, x tensor x, z tensor z, and product of these using that identity you answer in the poll, you will get minus y tensor y. So this is called a stabilizer group, which is basically a group of Pauli operators that mutually commute. Linear algebra tells us that whenever two Hermitian matrices commute, they can be simultaneously diagonalized, which means there is a common set of eigenvectors for all these matrices. So let's see a concrete representation of the eigenvectors for these matrices. For these matrices, the eigenbasis is called the Bell basis, which consists of these four Bell states or EPR pairs. So this is the canonical representation, phi plus, phi minus, psi plus, and psi minus. And here we have two qubits. So there is actually a tensor product in between. So this is 0 tensor 0 plus 1 tensor 1 divided by square root of 2. So this is actually, you start with 0 and 1, which are length 2 vectors, like I said before. When you take tensor products, these become length 4 vectors. And these are column vectors, not row vectors. So you have these four Bell states, and you can check their eigenvalues. So here is one example. So you use the same property that I showed you before. And if you apply x tensor x to phi plus, then using this property, you can apply x to each of those qubits in the superposition, and x flips 0. So you get 1, x flips 1, you get 0. And this is the same state that you started with before, which means x tensor x acting on phi plus give you plus 1 times the same state. So which means this is a plus 1 eigenstate of this operator. And similarly, you can check the eigenvalues of other operators on all these states. So now that we know the eigenvalues, what is the code? The code is actually the subspace of the full vector space of length 4 vectors that is spanned, that's a linear span of the plus 1 eigenvectors of this group. So in this case, if you go through the calculation, you will see that only phi plus has plus 1 eigenvalue with all of these operators, which means the subspace in this case is basically just a single state, phi plus. So I'll let you look at that for a few seconds. So we define stabilizers, which are basically commuting Pauli operators. And then we define eigenvectors, which are common to all of them. And we listed the eigenvectors here. And you know how to compute the eigenvalues. And in this case, you can check that only phi plus has a plus 1 eigenvalue with all of these operators. It's sufficient to actually check only with the generators. So you can check that it has plus 1 eigenvalue with this as well as this. So now again, to warm you up, here is a poll question. So I have all the information on the left side that you need. I want you to calculate what are the eigenvalues of the state psi minus, which is 0, 1, minus 1, 0, with respect to x tensor x and z tensor z. Okay, so as many of you got right, so the option is D. So you can check that. And I think for ZZ, it was maybe obvious for everyone. There was some confusion with option B, but the tricky part is you have 0, 1, minus 1, 0. So when you do XX, you actually get 1, 0, minus 0, 1. So if you take the minus out, then you get minus psi minus. So so that was the only change, but I think it's clear now. Okay, so let's proceed.
So actually, there's a question. Sorry to interrupt.
Yeah.
What is meant by a stabilizer group and why they are important?
Okay, so great question. So a stabilizer group is any so a group is a mathematical object. So it's composed of a set of generators, and the group of elements, which is basically a set, is all products of those generators. So for us, a stabilizer group means it's a group generated by polymatrices that commute, right? So we saw the commutativity condition earlier. So in this case, we had X tensor X and Z tensor Z, which commute. And so that causes, that forms the group. Now, we'll see shortly how we can translate these groups into more realistic codes. And then hopefully you'll see how error correction comes from this. Okay, so now, so we started with this stabilizer group. We had two generators, but we saw that there was only one state that was that had a +1 eigenvalue with both of them. So we didn't have a very interesting code space. So how can you form more interesting codes? For example, you could drop one of those generators. So now I have a smaller group. I only have one operation inside it. So it's Z tensor Z. So when you remove this, what happens is that you started with these 4 eigenstates for those commuting polymatrices, but now you enforce the condition that you only want +1 eigenvalues of Z tensor Z. That rules out psi plus and psi minus, and you're only left with phi plus and phi minus. Both of them have a +1 eigenvalue for Z tensor Z. And you define your code as the subspace spanned by these two vectors. So if you have an arbitrary single qubit state, alpha 0 plus beta 1, when you encode into this 2-qubit code, you actually make them alpha times phi plus beta times phi minus. And you can verify for yourself that for any alpha beta, this state has +1 eigenvalue with Z tensor Z. And you can also change basis, which we'll do for convenience. So you can change basis from this Bell basis back to the standard basis, 0, 0 plus 1, 1, which means your parameters change. So this is how you encode into the code. You take an arbitrary single qubit. In this case, you have a subspace spanned by 2 states, and you can form a linear combination, and that's your code. And your parity check is basically Z tensor Z. So every time you measure the eigenvalue of Z tensor Z, you're supposed to get +1. If you get -1, that's your syndrome and something went wrong. So you'll see that now. Okay, so in this case, you have one logical qubit encoded into 2 physical qubits. So I have the same thing here, but represented as an encoding operation, which is a single control knot. So the property of the control knot is that when the control qubit is 0, it doesn't do anything to the target, so you get 0, 0. But when the control qubit is 1, it flips the target, you get 1, 1. And for convenience, I've dropped the primes from alpha and beta, so I'm just using alpha beta as inputs. That's just for, but this is what you actually get when you encode alpha 0 plus beta 1 using this circuit. Okay, so this is your encoding map. And now let's look at how you can operate on this information. So on the left side, you have this 1 qubit of information. So if you wanted to flip that, you can apply X. If you wanted to do a phase flip, you apply Z. We saw this before. But now you've encoded it into this state. How can you realize the same thing by operating on these physical qubits? Those are exactly these operators. So if you do XX, meaning X tensor X on this 2-qubit state, you see that what you actually get is the encoding of the single X acting on the logical qubit. So this is the equivalent operation that causes the same action as flipping the logical qubit. Similarly, Zi or Z tensor I is the physical operation that realizes the logical Z. And so we call these the logical poly operators for the code. So these are the operators which, when acting on the physical qubits, cause the respective logical actions. Now, the synthesis of logical operators, which I mentioned in my first slide, is basically you have to take a universal set of quantum gates, which means the Hadamard, the T, and the C naught, and you have to translate them like this, but those become much more non-trivial, so we won't get into that in this course, but this is the idea you should have. Those are basic, so the logical operators are basically things acting on these physical qubits that realize whatever operation you want on the information. So here is the next poll question. So you have the stabilizer group, you know that X and Z anti-commute, and you have the logical operators for this code, X tensor X or Z tensor I. Now I want you to compare X bar and Z bar, X tensor X and Z tensor I, and tell me if they commute. And similarly, tell me if X bar and Z bar commute or anti-commute with the stabilizers.
In the meantime, there was a nice question that I've answered, but maybe you can add something on top. Why do we choose the subspace associated with the +1 eigenvalue?
Could you repeat the question?
Why do we choose the subspace
Oh,
associated
okay.
with +1 eigenvalue?
Yeah, that's just a convention. So yeah, so we just say that, you can, for example, fix that you like the -1 eigenvalue. So maybe you can pick all the states that have -1 eigenvalue with all the stabilizers. So that's just a convention. So it's just a standard way of defining the code as the +1 eigenspace of all the stabilizers.
Yeah, and then other people have trouble seeing the
So,
options.
okay, so maybe we'll just end the poll and I'll clarify what the answer is. Okay, so in this case, hopefully you were able to compute that, XX and ZI. So the first X anti-commutes with the first Z, and there's a tensor product in between, and X commutes with I. So so overall you get a minus sign. So X bar and Z bar anti-commute. But if you take X tensor X, obviously, commutes with both of these. If you take Z tensor I, it commutes with Z tensor Z, but it anti-commutes with X tensor X for the same reason. So this is a property that generalizes, meaning that whenever you have logical X and logical Z on the same logical qubit, they will anti-commute, but all logical operators will always commute with all the stabilizers. So this is a property you want to remember for all stabilizer codes. That was the point of the question. Okay, so let's get back to the code that we were looking at. Now we already discussed that poly operators form an orthogonal basis, which means I can kind of think of all channels as some combination of poly errors, which means we can just design codes for channels that only introduce poly errors on the qubits. And then hopefully the code will work as well for other channels. So there are like more detailed theorems on that. So I'm being a little hand wavy here, but that's the essential intuition. Because you can represent other operators as a linear combination of poly operators, it's a good idea to design codes for poly errors. So let's look at a concrete example. So let's say on this code, you have an error. You have a bit flip X acting on the first qubit, which means the state changes from 0, 0 plus 1, 1 to 1, 0 plus 0, 1. It flips the first qubit. Now, how do you know that something wrong happened? You measure the eigenvalue of Z tensor Z. This is basically the property that the state belongs to the code. However, this state does not belong to the code, so you will actually get a -1 syndrome in this case. And then your decoder can estimate what the error was. So let's discuss this bit more carefully. So here is the encoding. And after the encoding, let's say a single error occurs. This is the state. You measure the syndrome. So what happens? You're measuring eigenvalue of the error state with respect to the stabilizers. So you can actually do this computation. So you start with the error state. You want to measure the eigenvalue of ZZ. So you do this. However, now this error state can be expanded as X tensor I acting on the actual code state. Now you can compare Z tensor Z and X tensor I, and you know that they anti-commute. So you can reverse the order, you get a -1 sign. And then now you have a stabilizer acting on the state. That doesn't change the state. So you get back psi bar, and this xi was the error, E, and so you get back E psi bar. So effectively, if you compute the leftmost and rightmost expressions, you see that ZZ acting on the error state is -1 times the error state. So -1 is the syndrome. But if you look at the middle, you see that basically the -1 came from the commutativity of the error and the stabilizer. So if the error commutes with the stabilizer, you will get a +1. If it anti-commutes, like in this case, you get a -1.
So actually, can I interrupt you? There are many questions on the commutation relations between logical Z and XX. Can
Okay.
you maybe repeat that concept?
Okay. So let's go back to logical Z and XX. So here is so remember that this is X tensor X and this is Z tensor I. Now let me go back. So here you see that X and Z anti-commute. So XZ is -ZX. So if I expand this, I have X tensor X and Z tensor I. And because of the tensor product property, I can compare the first X and first Z, and then the second X and second I. Now the X and Z anti-commute, so you get a -1. But the X commutes with the identity because X times I is I times X. And so overall, you get a single -1. And that's why we say that X bar and Z bar anti-commute. So this is the same thing that we did earlier for X tensor X and Z tensor Z, but just a little different. So maybe I'll go all the way back. So here, as you can see, right? So yeah, so we use these commutativity properties to say that, in this case, we had X tensor X and Z tensor Z. We say that XZ anti-commute, so you get -ZX. Similarly on the bottom side, but then the -1 squares to the +1. So you just get Z tensor Z, X tensor X. In our example, we have the logical X being X tensor X and the logical Z being Z tensor I. And so on the second line, because you have an I here, you won't get a -1. So you'll get only a single -1. So that retains at the end. That's all that happened.
So actually, I keep receiving questions on this.
Okay.
Maybe when you define the logical operator to be ZI, since a logical should commute with all the stabilizers, it's not clear how XX and ZI commute.
Oh, I see. Yes, I think that was a typo. My mistake. Okay, so the mistake here was the following. So I actually removed the X tensor X stabilizer. So this new code only has one stabilizer, Z tensor Z. And so ignore this XX. I think that was the issue. So ignore this XX. It has a single stabilizer Z tensor Z. And then ZI commutes with that, XX commutes with that, and XX anti-commutes with ZI. So sorry, so this XX should not be there. Let me make a note of that. Thanks. Sorry for the confusion. So let's proceed with our error analysis. Okay, so we had this error, and you see that. So the point I want to make here is that the eigenvalue of the state after the error basically comes from whether the error commutes or anti-commutes with the stabilizer. Okay, and then what does the decoder do? Just like we saw in Michele's part for classical error correction, it takes syndrome as input and then tries to compute the most likely poly error that could have caused the syndrome. So in this case, you see that xi was the true error, but it's reasonable for the decoder to estimate xi as the error because it's a single qubit error. So it's a simplest possible error that causes the syndrome. So if the true error was xi, and if the decoder also estimates xi, then xi squares to identity, and then you get back the code state. So this is correct decoding. So you took the -1 syndrome, you estimated the error as xi, which turns out to be the same as the true error, and so you corrected the error properly. However, here is a catch. In this case, the decoder can also estimate ix to be the error, because that's also a single qubit error, and that also has a -1 syndrome. You can double check that because it anti-commutes with ZZ. So in this case, if you actually correct the xi with an ix, then effectively you did an xx, which is a logical x operator for this code, which means you unknowingly you changed the state from psi bar to x bar times psi bar. So you caused a logical error and the decoder basically failed. So this is exactly analogous to that 3-bit repetition example that Michele told you. So if the channel introduced 2 errors in that case, you could not correct it. And this is the same phenomenon in the quantum case. So here is the next poll question. So here I have the right stabilizer group. So it's only ZZ. So when you have the logical operators, and the syndrome is basically the commutativity of the error with the stabilizers. And then the decoder takes the syndrome and outputs the most likely error. So now can you answer this question? So these poll questions are not showing up properly. Can you all see the answers in the poll?
No, I cannot see the answers actually, but hopefully the other polls would be fine.
Okay.
You should just see the options of A, B, C, and D.
No, I actually see like 1, and then it kind of tries to restate the question. And then it says error dash correctable, single choice.
Yeah, I'm receiving many feedbacks that people cannot see the answers
Okay, so
actually.
let's end the poll. Let's just proceed. So again, so here, so the true error was Z tensor I. As you might have rightly computed, the syndrome in this case is +1 because Zi commutes with ZZ. In fact, Zi is logical, so we know that it commutes. What will the decoder estimate in this case? It basically has a perfect syndrome. So it just thinks that nothing happened, and therefore you cannot correct the error. So this is, again, a general phenomenon. Whenever the actual error is a logical operator, you can never detect it because your syndrome will be perfect. It will commute with all the stabilizers. The syndrome will be perfect. And so logical operators, if they happen to be the error, then you cannot correct them. Okay, so now hopefully you got the basic idea of error correction, right? So you know how to generate a small code. But this code was kind of trivial, meaning that it cannot correct many errors. It's not very interesting. Now, in Michele's part, we saw that there's a very rich theory of classical codes and decoders. Now, how can we leverage that in the quantum case? To do that, we need to make a bridge from quantum to classical error correction. So here is how we do it. So you take any Hermitian polymatrix, right? Here in this example, I have X tensor, Z tensor, Y. And then we are going to map them into a pair of binary vectors. And this binary representation gives us the bridge to classical error correction. So I will wrap these binary vectors A and B in this notation of E, which has some mathematical meaning, but we won't get into that. So what is A? So A is the X component of the poly operator. So wherever you see an X, you put a 1. Y, because it's a combination of X and Z, you still have a 1. For pure Z, you put a 0. So A is basically the X component of a poly operator, and B similarly is the Z component. So hopefully it's clear that wherever you have a X, you'll have a 0. If you have a z or a y, you put a 1. And so this pair uniquely represents this Hermitian Pauli operator. And we are ignoring faces. So if you have a plus sign or minus sign or plus I or minus I, that is not captured in this mapping, and we won't need that for now. Okay, so now we have mapped these Pauli operators to binary vectors. That's great. But is this just kind of like a simple shorthand notation, or is it more useful? Turns out it's more useful. For example, how can you check if these two operators commute using this binary representation? Well, you just compare, right? So if you just compare them position by position, you know that X and Z anti-commute, Z and Z commute, Y and X anti-commute. So overall, you know that they anti-commute. But how can you see that in the binary representation? First, you compare the X part of the first operator with the Z part of the second, because X and Z anti-commute. Similarly, you compare the Z part of the first operator with the X part of the second. And so you can exactly do that. So this is AB, let's call this CD. The way you compute whether they commute or not is using this so-called symplectic inner product, where if you have a pair of vectors, AB and CD, the symplectic inner product is basically the inner product between A and D plus inner product between B and C, and then you finally take modulo 2. So effectively, this is an XOR. So if this is 0, what does it mean? It means that you have an even number of X's and Z's in this computation overlapping. If you know that even number of X's and Z's will give you an overall plus sign, but an odd number of XZ pairs will give you a minus sign. And that becomes 1 in this binary inner product. So here is the inner product explicitly computed in this case. So this is A and this is B. And so this represents X in the first operator. This represents Z in the second operator. And so X and Z anti-commute. So 1 times 1 becomes 1. 0 times 1 is 0. 1 times 0 is 0. So overall you get 1. And this represents a single XZ overlap. Similarly, in the second part, you have a single ZX overlap. But there are two XZ pairs, and so they commute. So hopefully this inner product is clear.
Actually, could you go through actually that binary to Pauli mapping again?
Okay, so let's go back. Yeah. So if you see in the top, so whenever you have a Pauli operator, it's a tensor product, so it acts individually on each qubit. Now, the way you map them to binary is whenever you have an X acting on a qubit, in that particular position, you put a 1 in A and a 0 in B, because A represents the X component and B represents the Z component. Similarly, when you have a Z, you put a 0 in A and 1 in B. When you have a Y, you put a 1 in both places because it's a combination of X and Z. So overall, that's how you get the pair of binary vectors. And I did this once for XZY. And similarly for ZZX, you see that, so Z, Z, no Z, and then no X, no X, X. So that's how you get the binary representations. And once you have the binary representation, you can name them A, B, C, D, and you can compute the overlaps using this inner product. And if the inner product is 0 mod 2, then they commute. If it's 1 mod 2, they anti-commute. And so here is how you, so everything, so all these binary vectors are always row vectors, as you saw in Michele's part, and we'll use the same notation in my part. And so when you put a transpose, it becomes a column vector, and then you do the inner product, and finally you do XOR. So hopefully now things are clear. So let's give you some practice. So can you compute the binary representations for these two Pauli operators? So again, it's X tensor X, and this is Z tensor I. Compute the binary representation for each of them, and then tell me what is their symplectic inner product. So I'll give you everything you need on the left-hand side. Are there further questions, Michele?
Yeah, one question is how to prove the symplectic inner product lemma.
Great question. So maybe I'll wait for the poll question to end, and then I can tell you how to do that. So I think most of you got it right. So I think the binary representation maybe was not so difficult. Maybe the inner product was a little confusing. So in this case, what happens is, so here is the answer. So yeah, so instead of this example, you have 1, 1, 1, for example, and then you compare that with 1, 1, 0, which is here. So the only change here is you have 1 times 1 plus 1 times 1 plus 1 times 0. So you get 2 in the first thing. And then for the second part, you just get 0 because this is all 0, this is all 0. You just get 0 for this part. So you get 2, which is 0 modulo 2, which is why the inner product is 0. So hopefully the binary representation and the symplectic inner product are easy. This will be the most technical part. So hopefully it's okay. Great. So now let's get to codes. Okay, so now how will we form quantum versions of parity check matrices? Okay, so let's
Sorry,
take
Narayanan, just to remind you about the answer.
the answer. Okay, so so how do you prove this lemma? Good question. So yeah, it's kind of taking that logic that x's and z's anti-commute. So that's essentially what you'll use to prove the lemma. So you will just argue that every position of A represents an X or a Y in the first operator, and every position of D represents a Z or a Y in the second operator. And so this technically represents an X. So you have the inner product. So whenever you have a 1 here as well as a 1 in the same position in D, that means an X and Z are overlapping. Now, if it was a Y, then you will also have 1 here and 1 here. So you will also do that in a product 1 times 1. And so they will cancel because Y commutes with Y. And so you will just keep doing this argument for every position. And that's how you prove the lemma. Okay. So now that we are done with the poll, so let's get a parity check matrices. So I'm extending the 2-qubit code that we had to a 3-qubit code now. Now we have 2 stabilizers, Z tensor I and I tensor Z, and you can tell that they commute. So they form valid stabilizers. Now I'm going to do the binary representation. So they are only Z's. So the A part is 0 and the B part is clear, and similarly for the other. So these are the binary representation. Now, how do you form a parity check matrix? You just line up these rows. So each row of the parity check matrix for the code is composed of the binary representation of the respective stabilizer. So the first stabilizer, A1, B1, goes here. So this is A1 and this is B1. And the second stabilizer, A2, B2, goes A2, B2. Now we divide this into the X part and the Z part just for visual purposes. There's not like a physical meaning to this, but so if you just divide, you can call the X part HA and the Z part HB. And how do you make sure that the stabilizers commute? You have to compute the symplectic inner product between the stabilizers. And that's what this equation does. So it compares the X part and Z part with X part. And so this makes, if this is 0 on the right side, then you make sure that all stabilizers commute. Now recall that the syndrome for a quantum code is basically the commutation relations of the error, which was in that example was xi, and you compare that with each stabilizer, and that's where you get the sign for the syndrome. And so you can just again do that using the symplectic inner product. So the syndrome is basically the symplectic inner product of the error, which I'm calling E of C comma D here. And I'm computing the symplectic inner product with each stabilizer and lining up them as a column vector. So the column vector here consists of zeros and ones. And if it's all zeros, it's a perfect syndrome. So you say nothing wrong happened. If anything is 1, then you have to run a decoder and estimate what the error is. So this is how you compute syndrome for quantum stabilizer codes using the binary notation. Again, all you're doing is just computing commutativity and anti-commutativity. Okay, so we saw a lot about the 2-qubit code at the beginning, starting from Bell states, where we removed a stabilizer. And you can compare them line by line with this new 3-qubit code that I just introduced. So in this case, you have, again, 2 basis states, phi plus and phi minus, but now they have 3 qubits. Again, from the stabilizer, so you take, for these 3 qubits, these are all the full stabilizers, but you remove one stabilizer so that they have +1 eigenvalues with all of them. And you can check that phi plus and phi minus have +1 eigenvalues with these 2 stabilizers. And then here is the encoding map, just like before. Again, and this is the encoding map. And you can also translate the logical operators from the 2-qubit to the 3-qubit case. So you see that you can basically generalize this idea, even though this 3-qubit code is also quite simple. Now, here is a word of caution. So some of you might have already noticed that this 3-qubit code is a linear combination of 0, 0, 0 and 1, 1, 1. So maybe you're thinking that this is the quantum version of the 313 repetition code that Michele introduced right at the beginning of his talk. It's not true, because if you just take a single qubit, alpha 0 plus beta 1, and repeat it 3 times, meaning you take a tensor product of 3 copies of this, you won't get the same thing. So in fact, quantum mechanics forbids you from cloning any qubit. So it says there is a no cloning theorem. It's a short proof, which shows that an arbitrary quantum state cannot be copied. So there is no control C for quantum information in general. And so this 3-qubit code is kind of similar to the repetition code, but it's not a quantum repetition code. So and you can convince yourselves of this by just computing the tensor product of 3 copies of psi and expanding that, you won't get this. Okay, so now I told you how to compute syndromes using the symplectic inner product, but in the lab, how do you do it, right? So in the lab, you have built these qubits using atoms or whatever, and then you encoded them into a code, and then somehow you need a way of actually measuring the syndrome. You cannot compute symplectic inner product in the lab. So how do you do it? So this is how you build circuits to compute the syndrome. So let's say you start with a perfect code state and then an error happens. You measure the first stabilizer, meaning you measure the eigenvalue of the first stabilizer. And this is a circuit that does that. I won't go into the explanation, but basically for every Z you have, you do a C0 from the code qubit to an ancillary qubit initialized in the 0 state. So you have 2 Z's in this case, so you have 2 C0s, and then you have an identity, so you don't do anything. And then you measure this ancillary qubit in the Z basis. So this is a quantum measurement, and you're measuring the operator Z, which has eigenvalues +1 and -1, and that your result will be +1 or -1. So in this case, in fact, this X is an error, and you can show that it will propagate to this C0. So the error propagate through this first C0 and flips this 0 to a 1. So when you measure the eigenvalue Z, you get a -1 in this case. But the X does not propagate into the second stabilizer because clearly there is no C0 from the first qubit to the ancillary qubit. And so the X doesn't affect the second stabilizer, and so you get a +1. And as you can see that this is basically computing how many, if you have an odd number of X's on the ancillary qubit through the C0s, you will get a 1, so you get a -1 result. But if you have an even number of X's going into the ancilla, then you get a +1, which is exactly the same as computing the overlap of the error with each of the stabilizers. So this physical circuit, the way it generates +1s or -1s, is exactly the same as computing whether the error commutes or anti-commute with the stabilizer. And this is just the physical proof of that. Okay, so in this case, you just compute the syndrome using the same equation that I showed before. In this case, the error is X tensor I tensor I. Okay, good. Now, what happens to the other type of error? So if you have a Z error, it turns out that Z does not propagate through the C naught. And when you measure these stabilizers, it will not show up anywhere. You get a +1 result for both stabilizers. And so you will never see the error. And we know that Z commutes with Z operators. So even from commutativity standpoint, you know that the error commutes with the stabilizers. Now here is where we define the minimum distance of code. So remember the classical minimum distance that Michele defined. This is the quantum version of that, which is equivalent. So it's basically defined as the minimum poly weight. And poly weight is basically the number of qubits in which a poly operator acts non-trivially. So ZZI, the poly weight is 2. So it's defined as the minimum weight of an undetectable error, meaning so the channel must act on the minimum distance number of qubits for the error to go undetected, meaning it actually changes your system, but you never see it. So it's a problematic error, but you don't see it. That's the reason behind this definition. And if you think about it a little bit, you will see that the classical minimum distance that Michele defined is equivalent to the same definition. And we already saw in that poll question that when you have a logical operator that's the error, you cannot detect it because it has a perfect syndrome. And that's why you have an equality. So the minimum weight of an undetectable error is the same as the minimum weight of a logical operator. And we know the logical operators for this code. And because the logical Z operator only has a single Z, the minimum distance of the code is 1. Hopefully I'll leave this slide for a few seconds so that you can kind of absorb what I just said. Okay, so this is how you compute the minimum distance of a code. If you know all the logical operators, it's the minimum weight of a logical operator. Here is the next poll question. So you have the code definition using the parity-check matrix, and you have the logical operators. And here I want you to compute the syndrome for the errors E1 and E2. So X tensor I tensor X and I tensor X tensor I. Can you basically write binary vectors for this, do the inner product, and then give what the answer is. If you feel more comfortable doing commutativity directly, you can also just compare the errors with the stabilizers. So the stabilizers are ZZI and IZZ. You can also do the commutativity check directly, or you can do the inner product. Okay, maybe we can end the poll. I'll clarify what the answer is. So it seems like there was a confusion between A and C. So if you compute the actual inner products, you will see that, XIX, if you compare with the first stabilizer, which is ZZI, you see that, if you compare XIX with ZZI, X and Z on the first qubit overlap. So that's anti-commuting. And then on the other qubits, you have nothing like that. So this anti-commutes with the first stabilizer, as well as the second stabilizer. So if you compare with IZZ, again, you have one anti-commutativity, so it's 1, 1. And similarly, you can check for IXI, it also anti-commutes with both stabilizers. So maybe it just takes a little while, but it's a fairly straightforward calculation. So here is another poll question. I want you to do the same using errors ZIZ and IZI. Hopefully this is easier. Yeah, so I think, yeah, the majority got it right. So it's option D. So because your errors are also Z operators, they obviously commute with the stabilizers, which are Z operators. What I wanted to highlight here is that so these Z operators are actually logical Z operators. So as you can see, IZI is a logical Z operator, and ZIZ is also a logical Z operator. And so when you have logical operators, they commute with stabilizers, you cannot detect them. That's what I wanted to highlight. Okay, so now this is a simple code. It's more non-trivial than the 2-qubit code, but still it can only correct one error of X type. If you have any error of Z type, it cannot do anything, right? So how can you modify this to a code that can correct at least one type of error, at least one error of any type? And the key idea there, the key insight is that you can concatenate the 3-qubit code with the X type version of itself. I'll show you what that means. This is what Peter Shor did in the mid-90s, and that was the first concrete example of a working quantum error correcting code. So until then, people were skeptical whether error correction can work in the quantum case, but this established quantum error correction as a field. So here is Shor's idea. So this is the encoding map for Shor's 9-qubit code. So you have a single qubit at the input, and here is a giant encoding map. Now you do identify, this piece which you have seen before. This is this 3-qubit code that we just saw. That's the encoding for that. But before you use that encoding, you have to use first the X version of the same code. The stabilizers and logicals are given. As you can see, you just swap X's with Z's. And so this is a different 3-qubit code. It's called the phase flip code. So you first encode into the phase flip code, which has an extra Hadamard in the encoding. And then you take each of the 3 qubits of the encoded phase flip code and encode it using the bit flip code. So this is what we mean by concatenation. You do 2 rounds of encoding using different codes. And you can show in this case that this code corrects one error of any type, and that's why the distance is 3, because you can correct d minus 1 over 2 errors, like Michele showed before. And in this case, you have 9 minus 1, so n is 9, k is 1, so you have 8 redundant things. Those are the stabilizer generators. So 6 of them come from just 3 copies of the bit flip code. So you have these 2 stabilizers, you have 3 copies of them, so that's 6 of them. And then the 2 X-type stabilizers comes from the X1s, but it's a concatenation. So it's not the stabilizers are not exactly like this. You have to replace each X with the logical X of the inner code. So in fact, this X will become XXX, this X will become again XXX, and this I becomes III. So here I have X from 1 to 6 and I here. That's the first stabilizer. The next X stabilizer is I here and X is there. So this is the idea of concatenation. Another way of visualizing it is you can put the qubits in a grid. So you combine, the 3 qubits in each row to form a logical qubit of the bit flip code. So you have 3 logical qubits of the bit flip code, and then you have an outer round of encoding, which is the phase flip code. This is the outer concatenation. So this is another way of visualizing any concatenated code. So this is the first and one of the most important examples of quantum error correction. Now we can also go to other codes. So here is the Steen 7-qubit code. Now from Michele's lecture, you have seen the Hamming code, which has this parity check matrix. All you do to get the Steen code is you use the parity check matrix in this block fashion. So this is a quantum parity check matrix, but we just divide it into a block diagonal form and use the Hamming code for the X part and then for the Z part. You can do a commutativity check like I showed you before. It works out. And the logical poly operators in this case are basically X on all qubits, and the logical Z is Z on all qubits. So this is the Steen code. Now you might have the question of, okay, so the distance is 3. We define the distance as the minimum weight of a logical operator. But here you're showing me a logical operator of weight 7, not 3. So how does this work? Here is the trick. Now, if you see the stabilizer, right? So the stabilizer coming from any of these rows, but for example, the last row, you get 2 stabilizers. So either the X type or the Z type from the top row, the top part and the bottom part. These are weight 4. Now what you can do is you can take any logical operator and multiply it by a stabilizer, because the stabilizer acting on the state doesn't do anything, because the state is a +1 eigenstate. And so you can take any logical operator, multiply by a stabilizer, and in this case, you can reduce the weight. And now you see that the weight is 3. And that's why the distance is 3. It's the minimum weight of a logical operator. So this is a common trick. You can always multiply stabilizers with logical operators and nothing changes. All right, great. How do you decode this code? Again, you can compute the syndrome. In this case, it simplifies into two distinct syndromes. One, using the X stabilizers, you get a syndrome for the Z errors, and then you use the Z stabilizers to get a syndrome for the X errors. Right? So use the what does the decoder do? It can take the X syndrome, compute the Z error, or they take the Z syndrome, compute the X error. So therefore, all you're doing is that you're just decoding the Hamming code once for each type of error. So this is like you see, we wanted to make a bridge to classical error correction and kind of leverage those ideas. Here is how we do it. Right? Now, if the errors are correlated, so here we are treating the X and Z errors as independent. If the errors are correlated, then this kind of decoding will be suboptimal, and you have to use somehow a correlated way of decoding, which is more non-trivial. So just to remind you, this was the standard array that Michele showed you before. You can just use it once for each type of error to decode the quantum Stein code using the classical Hamming code. Okay, next poll question. So here I want you to think a little bit about, so now we have seen what errors are correctable, right? So if you have a logical operator that's an error, then you cannot correct it. But other errors, you might be able to correct. So here I want you to consider all poly errors that a code can correct using the standard array, like for the Stein code. Then which of the following is true? Remember, this is a correctable set of poly errors. Think of which errors you can correct and which errors you cannot.
So maybe in the meantime, Narayanan, maybe you can answer or try to answer this question about books for solving quantum query problems, which is something I'm not aware of.
I'm not clear about the question, so I don't know what query. Maybe it's related to complexity, like computational complexity kind of things. I'm not too
Yes, I think so.
Yeah, so there's a field called quantum complexity theory, which is where maybe people talk about query complexity and things like that. That's where I would suggest to look if that's what you mean. So this is a bit of a tricky question. So and I see that confusion in the poll. Okay, in the interest of time, let's close the poll. So great. So yeah, so this is what I want to bring up. So I know that B and C are very close, and that's very natural. So the reason is the following. So it is completely reasonable to guess that B was the answer, but the tricky part is unique. That's the word that distinguishes it, that makes the statement false. So if I removed unique, it's true that all of those errors will have a non-trivial syndrome. And from a classical point of view, unique is the right word, and B would be right. Right? Because if you have a correctable set of poly errors, it means you can distinguish all the errors, which means all of them must have a unique syndrome. But in quantum, we just saw that stabilizers don't change things. So if you have two errors, which differ only by a stabilizer, like one error is the other error times a stabilizer, then they both have the same syndrome because that extra stabilizer multiplication doesn't change the commutativity because stabilizers commute with stabilizers. So both of those errors will have the same syndrome. And indeed, they have the same effect on the code because if you multiply an error by a stabilizer and act on the state doesn't change because the stabilizer fixes the state. So this is why not all errors need to have a unique syndrome, but two errors in the set with the same syndrome must multiply to form a stabilizer. Only then they're equivalent. So this is the idea of degenerate errors in quantum, meaning that there are multiple errors which have the same effect on the code because they differ by stabilizers. Okay, so that's the concept I wanted to highlight with this question. Okay, so now let's generalize the Stein code. So on the left, you have everything that we have about the Stein code. You can generalize this to a class of codes called the Kaldebang-Shor Stein codes, or CSS codes for short. So all you have to do is you find a pair of classical parity check matrices, Hx and Hz, such that they are orthogonal to each other, because that's when you will have the quantum commutativity satisfied. And then you compute the syndrome separately using X stabilizers and Z stabilizers. And then the logical operators are given by these relations. Okay. And finally, K, which is the number of logical qubits, is N minus the rank of the X stabilizers and the rank of the Z stabilizers. And D is the minimum weight of any logical operator, like we defined before. So this class of CSS codes is super useful. And so here is another kind of visual way of seeing this. So you can think of a CSS code as a pair of classical codes, CZ and CX, with some parameters. And they have subcodes. So the dual of CZ is contained inside CX. So that's what this line means. It means this code is a subset of the big code. Similarly, the dual of CX lies inside CZ. And these two subcodes are the ones that give you the X stabilizers and Z stabilizers. So the HX and HZ are actually coming from this. They are parity check matrices for the top codes or generator matrices for their dual codes. The logicals live in this mod space. So you know the concept of generator matrix. So if you compute the generator matrix of CZ and you remove the HX part from that because it's a subcode, then the remaining gives you the logical X. Similarly, the logical Z. And then you can use these parameters to compute K in terms of the parameters of the classical codes. Finally, if you want to make this CSS code LDPC, then you have to use a pair of classical LDPC codes that satisfy this HX HZ transpose 0 constraint. So that's how you make quantum LDPC codes. So maybe that was a little fast. I'll stay for a few seconds. So you can translate a pair of classical codes that satisfy this orthogonal property into a quantum CSS code. And so this gives us access to the rich theory of classical codes. So here is the standard quantum example called the surface code. Now I'm pictorially representing this. So each of these white circles represent the physical qubits of the code, and the squares represent either X stabilizers or Z stabilizers. So in fact, the blue represents a Z stabilizer, which means that you will have, so for example, this blue stabilizer is a Z stabilizer on these 4 qubits. So Z, 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 Z. Similarly, this X is X, 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 X. So all of the X and Z stabilizers are weight 4. And you see that the X stabilizer and the Z stabilizer overlap on 2 places. That's why they commute. Because each place they anti-commute and the anti-commutativity cancels. And so that's how the code is defined. And you can define this on different size lattices. So this example is on a 5x5 lattice. And these are the parameters for the code. Now let's look at some errors on this code. So here, for example, I'm showing you some different errors. So here on the top, you have an X stabilizer that gave a -1 syndrome because this neighboring qubit has a Z error. So this Z error anti-commutes with this X stabilizer. Similarly, here, for example, there is a single X error, but it anti-commutes with the neighboring Z stabilizers. So both of these stabilizers cause a -1 syndrome. On the right side is a sequence. So you have a sequence of 3 X errors, which means the middle stabilizers commute because you have 2 errors. But the end points is where you see the -1 syndrome. Similarly here, I have a sequence of Z errors. And so only the end X stabilizer anti-commutes, the middle ones will commute. So you see the pattern in the surface code that whenever you have a sequence of errors, only the endpoints flag the error, cause the syndrome. Now, how do you decode? So to decode, what we first do is you introduce these so-called virtual checks, which are only for the purposes of decoding. And then what you do is you generate a syndrome graph. So I take this anti-commuting X stabilizer and this anti-commuting X stabilizer, and I put them here. And then I add the virtual checks at the end of those rows, at both ends. And then I connect them with edges, and then I give weights for the edges. So what does the weight mean? So here, this weight 1 means that a single error, I mean, the path length between this virtual check and this physical check is 1, it's a single qubit. Whereas between this check and this check, you have to go through this whole path. So you have 1, 2, 3, 4, 5, 6 qubits. So only if all these 6 qubits were an error, these two will flag, right? So that's the logic. So you put an edge between those two checks, and you say the weight is 6. Similarly, you compute weights for all the other edges in the syndrome graph. Now, what's the point of making the syndrome graph? The idea of the minimum weight perfect matching decoder is to match the checks that flagged. So here we have 2 X stabilizers that flagged, and you want to see if we can pair them up with a single error of weight 6, or whether we should pair the checks with the virtual checks because those have lower weight errors, right? So you see the weights, and clearly 6 is much bigger. So if you run the minimum weight perfect matching algorithm, it will try to match this graph, and it will give you this matching graph, right? So it matched just check with this virtual check, so that has weight 2, because this check, if these 2 qubits were an error, they will flag the endpoints. So it will flag the virtual check and this physical check. And that's the same thing that happens on this side, except that you have this virtual check. So in fact, the decoder will actually match this check with this virtual check rather than the left side one. But on the top, it does the right thing because that's the smallest. The other side has a larger weight. So overall, the decoder failed because it corrected this 3-qubit error with this 2-qubit error, overall causing a logical error. Because in the previous slide, we saw that the logical operators are either horizontal or vertical. And in this case, the true error was on the left side, but it was beyond the capability of the decoder. And so it miscorrected the error, and it caused a logical error. So hopefully the idea of the surface code and matching are clear. And here comes the curve that I showed you at the beginning of my section. So this is the simulation of the surface code using this decoder. And you can find that in this paper. And as you can see, there is a threshold for the physical error rate. On the left side of the threshold, if you keep increasing the lattice size, meaning also the distance of the code, then the time to failure increases, meaning the code lives for longer. But on the other side of the threshold, if increasing the lattice size is a bad idea. So the threshold is an important property for a family of codes, and that's what I wanted to show you. So maybe I'll skip this question. So I'll share the slides with the poll questions later. In the interest of time, let me skip this. So then we have an extension of the surface code, which is the hypergraph product construction. So it's a little bit technical, but here are the basic ideas. So you form 2 HX and HZ matrices using a pair of classical codes, which have some parity check matrices. And we're using the tensor product so that you can compute HX HZ transpose almost directly using the tensor product property I showed in the beginning. And you can convince yourself that they actually commute. And the number of qubits in the code is given by the number of columns in this first part, plus the number of columns in the second part. That's where this count comes from. And then you can compute the number of logical qubits. And then you can also compute the distance of the code, which is the extension of the lattice size for the surface code. So the surface code clearly is a hypergraph product of 2 repetition codes. So you have a repetition code here, and then I have the transpose of that as CB, which means I'm replacing each circle with a square and each square with a circle. And then what happens is that whenever a circle and a square meet, you put a circle. Whenever a circle and a circle meet, you put a square. So this is a Z stabilizer. This is a data qubit. When a check and a check meet, you get an X stabilizer. When the check and a variable meet, you get a different kind of variable. So these are this is how you do the hypergraph product. And again, you can derive these parameters if you think a little more about this. But this hypergraph product construction is a very nice extension of the surface code, and it has produced a lot of interesting codes. So once you have these quantum LDPC codes, you can use the same kind of iterative decoder that Michele showed you, with a few caveats. First, there is no received sequence. So in Michele's bit flipping example, he worked with a received sequence, but here you only have to work with the syndrome. I think maybe he also used only the syndrome, but yeah, in quantum case, you only have the syndrome. Now, if there are no correlations between X and Z errors, then you can use two decoders. Otherwise, you have to use a correlated decoder if you have correlated errors. Now, if you look at the decoding curves, there are a few different things. So first, the decoding schedule. So when you do these check to variable and variable to check messages, you can do them as parallel updates or as serial updates. So they give very different performances, and you can see here. So the flooding is the parallel update, whereas the layered is the serial update. And you see that the serial does better in this case. Error floor, like Michele showed, for example, this parallel update decoder does floor at some point, meaning it saturates at some non-trivial error rate and it never decreases. Degeneracy is where two errors are equivalent, meaning they just differ by a stabilizer. And so degeneracy is a big issue in quantum, and kind of developing decoders that can take advantage of the degeneracy is still an open problem. So you can learn more about this in this paper by our collaborators. Finally, so here are some a brief list of very important recent quantum LDPC papers. You can check out these when I share the slides. But there was a flurry of work that has given us optimal quantum LDPC codes, meaning that the n, k, d parameters, the k and d scale optimally with n. So we know of optimal LDPC codes today, but how to implement them is still a very open area of research. And that's what I work on, for example. So from the surface code to good quantum LDPC codes, here is a comparison. So a lot of things about the surface code is known, but for LDPC codes, you have optimal parameters. You have quite good error thresholds. The decoding is fast, but doing these logical operations. So remember, kind of synthesizing that Hadamard, T, and C naught, those kind of things are very little is known. And they are also not geometrically local like the surface code, meaning that you have to connect qubits that are far apart. And so that's a challenge to come over. And finally, yeah, so the overhead coming from the surface code is too large. That's why even though it's mature, it's not very scalable. And then the question still remains whether we can take these optimal LDPC codes and scale them up with minimal overhead. And so here is maybe one question, and we'll stop with this. And finally, we have the last section by Sijie. Okay, I think we can close the poll. I think most of them got it right. Sorry for everyone else that was just about to answer, but I think everyone got it right. So all of these are reasons for why you should use quantum LDPC codes. Maybe the first point, because LDPC means it's sparse matrices, right? Meaning that each stabilizer only acts on a few qubits. And this is very important because if you remember that syndrome measurement circuit, each of those Z's or each of the X's will give a C naught, and you want to reduce the number of C naughts. And so that's why syndrome measurement is easier. And the other 2 points, I think you already know. Great. Summary. So here are the main parameters for both classical and quantum codes. And we looked at a concrete example of the bit flip code, where you first encode, then you have errors. when you have errors, they change the state and they propagate and change the syndrome. And then you take the syndrome measurement and you pass it to a decoder. So for LDPC codes, you can use Sabelief propagation and then decode. So that ends my section. We went a little over what I planned for, but hopefully you got the main ideas. Maybe we can take a break for a few minutes, and then Sijie will show you how this can be applied in quantum networks. But most of the big technical part is done. So Sijie's part will be much lighter. It's a lot of nice animation. So hopefully you enjoy and appreciate how this is applied to quantum networks. So we'll maybe start in 2-3 minutes.
So actually, before the break, there are some questions.
Sure.
So one question was about logical operators. And in particular, how can we think of them, especially in large codes? What is the interpretation that you can give to a logical operator?
Yeah, good question. So sometimes when you can visualize the code, you can visualize the logical operator. But for these more optimal LDPC codes, they are harder to visualize or intuit. But logical operators, think of their definition. They are basically operators on the qubits that commute with all the stabilizers, but they are not stabilizers themselves, right? So they're distinct from stabilizers, but they commute with all stabilizers. So usually for LDPC codes, they are high weight operators. So the stabilizers are low weight. So the syndrome measurement is easy. But the logical operators are high weight, meaning they act on many qubits, which is also why it's very hard for the channel to introduce a logical operator as the error and kind of mess up things. Because we saw that when the error is a logical operator, you cannot even detect the error. And so because logical operators are very high weight for LDPC codes, it's very hard for the channel to mess things up. But depending on the code construction, sometimes you can intuit about it, sometimes it's harder.
So I would also add on top of that I like to think of logical operators as code words. Like in the classical scenario, you have code words, and the minimum distance depend on the weight of the code words. And similarly, logical operators represent somehow, of course, with the some differences, but somehow the possible code words of your quantum code. So each different logical operators represent a state that your quantum information is in, essentially. And also another question is more like from a classical perspective. What are some of the problems encountered in quantum error correcting codes? For instance, in classical, we know that short cycles impact the way you create parity-check matrices. Are there similar effects in quantum?
Absolutely. So great question. It's true. So many of the issues we face in classical error correction also translate to quantum. So short cycles will be a problem for decoders. But in fact, in quantum, the problem is more pronounced because as you can see, maybe I won't go all the way back. But the problem is because of this commutativity condition that's necessary to make valid stabilizers, this symplectic inner product condition actually gives rise to cycles itself, because you need an even number of overlaps between stabilizers, which means if you make a Tanner graph for the whole stabilizers, those even overlap conditions for commutativity introduce short cycles in the graph, and so that's a problem. Again, but there are also new things that show up in quantum. For example, degenerate errors are a completely new phenomenon. So if you're aware of trapping sets or stopping sets for classical LDPC codes, you have a quantum, you have the same things appear in quantum, but you will also see new kind of trapping sets because of these new quantum phenomena. So many of those problems actually reappear here. So I see a question. So what are the exact paths in the surface code containing X or Z stabilizers for encoding and decoding process? I don't know what you mean by paths, but for decoding, for example, right? So when you have the surface code, as we saw that the errors cause the errors are kind of like linear chains on the code. Yeah, so the errors, as you can see here, are basically linear chains. So, and syndromes pop up only at the endpoints of the errors. So that's like the physical nature or topological nature of the errors. And that's what this minimum weight perfect matching algorithm leverages to match, different syndromes. And yeah, so that's how it translates the decoding. So stabilizer generator is just, like I said, stabilizers are commuting Pauli operators. And for the set of all commuting operators that you have in hand, you can usually form a set of generators, meaning every other operator in that group is a product of these generators. So that's what stabilizer generator means. Okay, so I think we should move on to the last part. So I'll stop sharing and then Sijie, you can start sharing. And so I will answer poll questions. I will answer Q&A, and Michele, if you could handle polls for the last part.
Yeah, absolutely.
Yeah, go ahead, Sijie.
Okay, so hello everyone. My name is Sijie Cheng, and I am a PhD student working with Professor Rengaswamy at the University of Arizona. After the first part, classical error correction by Michele, and the second part, quantum error correction by Professor Rengaswamy, I believe you now have a basic understanding of quantum error correction concepts. For my part, let's explore how to apply these concepts in real-world situations. Let's start with a brief overview of a 311-bit flip code. At the beginning, we have a quantum state. After encoding, we can get the coded state. If an error occurs, we can use the syndrome measurement to get the syndrome of error. If there's no error, the same quantum circuit can be used to get the sample stabilizers. From now on, we will focus on using the biostate as a tool to demonstrate quantum error correction applications. In fact, it is similar to the 311 code, but we concentrate on just 2 qubits. The key difference is that we can send these 2 parts to different locations to create a bio pair. Consider a bio pair between points A and B. The measurement will break up the pair. However, because the pair is entangled, measuring one part of the pair will create a demonstrative measurement result on the other side. For instance, if we have a biostate of 00 plus 11, and A measures a pair of biostate on X and gets plus 1, we can definitely say that if B measures his part on X, he will also get plus 1. Here, the plus state simply indicates a measurement on X resulting in plus 1. Interestingly, measure just one part is sufficient. The other part will automatically align to the same result without needing actual measurement. And these 2 situations are equivalent. In this part, since we are focusing on application rather than the core mathematics or quantum mechanics, I feel there is a very interesting way to introduce it. At the beginning, let us use some symbols to represent our learning so far, as they can be extremely helpful in grasping the key ideas of error correction in quantum networks. At first, uncoded state without errors will be represented by dots, and those with errors by stars. We will use square to represent stabilizer generators. You can imagine this as a box, and then placing an uncoded state inside turns it into a coded state without error, symbolizing the box's protective nature. A square with its corner cut off represents the coded state with error. Similarly, Small squares will denote the sign for stabilizers, and their cornerless versions will represent the symbol for error. These cut corners mean estimate errors. At the same time, we will use different arrows to represent the classical channels without error, the quantum channel without error, and the quantum channel with error, represent respectively. Next, these boxes will denote syndrome measurement, decoders, and correctors. And then the wavelengths with dots mean Bell states. And then the waveline represents the Bell pair without error, and the dashed lines for those with error. And the double lines will represent equality. Now, let's apply these symbols to some previously discussed concepts. First, give a stabilizer generator of stabilizers and a coded state with error. Using the measurement, we can get the syndrome of error. Second, given stabilizers, the sign for stabilizers and the syndrome for error. Using a decoder, we can get the estimated error. Finally, if the estimated error matches with the actual error, using the corrector, we can correct it to get the coded state without error. Okay, let's start. At the beginning, let us imagine a quantum network. Here, we will have a bunch of quantum nodes, which could be computers, sensors, or whatever. To simplify, we will discuss a network with just 2 nodes and one directional communications. This means we will transmit a quantum state with information from one node to another through a quantum channel. If the distance is short, there is a very low probability of getting an error. However, as the distance increases, channel noise intensifies, reducing fidelity and eventually leading to channel failure. Later, if we also want to do some quantum network operations, it will make the channel fail very quick. Therefore, we need a way to correct errors and increase the stability of quantum bits in the network. The process is known as quantum error correction. Okay, so let's go deeper. We will name one node Alice and the other Bob. If Alice sends an encoded state through a node quantum channel, Bob cannot correct the errors because the state's information is already lost. Thus, encoding is essential. Therefore, once Alice has an coded state, she can select a series of stabilizers and encoding. After recoding, she can get the coded state and sign for stabilizers. And then, Alice can send the stabilizer generators and sign to Bob through a classical channel, which is assumed to have no error inside. Next, Alice sends the coded state to Bob through a noisy quantum channel. Upon receiving the coded state with errors and the stabilizer generator from Alice, Bob can use a measurement quantum circuit to get the syndrome of error. Using the stabilizer, signs, and the syndrome for error, after decoding, Bob can get the estimated error. Finally, if the estimated error aligns with the actual error, Bob can correct it by using a quantum circuit to get the coded state without error. Finally, the coded state can successfully transfer from Alice to Bob. Throughout this process, most noise in quantum circuit could be ignored, except for the decoder, which is the core point for quantum error correction. A quick summary. The sending order is not important. Alice could first send the quantum state through a noisy quantum channel, followed by the stabilizer and signs through the classical channel. And then Bob can use the decoder to estimate error and correct it to recover the coded state. Now, this is the third poll question. So what is the primary purpose for the quantum error correction in quantum networks? All right, so almost get a good answer, correct answer. So the answer is D. The quantum error correction in quantum networks means the quantum error correction in quantum networks means correct errors caused by noise and operations in the quantum channels or quantum network to improve the stability of quantum bits. As I mentioned, the decoder is the core of quantum error correction. Ideally, it should work perfectly. However, there are two main problems that could lead to decoder failure, consequently causing the entire channel to fail. The first problem is the long distance. As distance increases, the coded state accumulates more errors, leading to what we call the decay problem. Once the number of errors is larger than the limit that the decoder can correct, it will fail. A typical solution is using repeaters. Between Alice and Bob, we can introduce a node called a repeater. Depending on the situation, the number of repeaters can be different, but we will focus on a single repeater scenario. First, Alice sends the coded state and the classical information to the repeater, which can use the decoder to estimate error and correct it. And then the repeater forwards the corrected coded state and classical information to Bob. Finally, Bob can use the decoder to estimate error and correct it again, successfully transferring the coded state from Alice to Bob. In summary, because long distance could trigger the decoder failure, we can use repeater to reduce the error correcting pressure on a single decoder by shortening the distance. Now, for the second poll question, what is the primary purpose for a quantum repeater? Okay, so most is good question, correct question. The answer is B. Let me put this one. The answer is B. The goal for the repeater is to solve the decay problem from the long distance. The rest of them are not the primary purpose. The second problem arises even the sufficient distance. Environmental factors can cause too many errors, leading to decoder failure. This is a problem we cannot fully solve. Thus, we need an alternative approach where decoder failure doesn't cause quantum channel failure. One solution is to perform decoding earlier than the actual communications. To understand this, let's revisit the properties of the BIOS state. At the beginning, Alice prepares a BIOS state and sends part of it to Bob through a quantum channel. Here, we assume the quantum channel is perfect. And then the parts of Alice and Bob form a BIOS pair. The mathematical form is in below, but I may not go deeper here. Importantly, if we have n BIOS pairs and a series of stabilizer generators, after mirroring, we can get a k-coded BIOS pairs and the stabilizer signs. The stabilizer measurement doesn't break up the BIOS pair, and the pairs are protected by stabilizers. Furthermore, if we only do measurement in the Alice part, the Bob part will also follow the rule. And these two situations are equivalent. Based on this property, we can go to the next point called teleportation. At the beginning, Alice and Bob generate several BIOS pairs. And then Alice wants to send a coded quantum state to Bob. After the operations and measurement between the coded state and one of the coded Bell pair, Alice can get the classical information that shows the difference between the coded state and the coded Bell pair. And then Alice needs only to send this classical information to Bob. Based on this information, Bob can transform another part of the coded Bell pair into the coded state that Alice wants to send. Be careful, we never observe what the coded state is, but the difference between the coded state and one of the coded Bell pair. During this process, we can use the Bell pair plus classical information to transfer the quantum state, and the information is in classical channel, but not in quantum channel. This idea will give us a new way to solve the decoder field problem. First, in a noisy quantum channel, we establish an imperfect Bell pair. Then, as with quantum error correction, Alice sends the stabilizers and their signs to Bob through a classical channel. Bob used the decoder to estimate and correct errors. If the decoder fails, the attempt is discarded. However, if successful, the Bell pair is retained. This process can improve the purity of the quantum state. When Alice is ready to transfer a coded state, she only needs to send the relevant classical information to Bob. Using this information and the Bell pair, Bob can retrieve the coded state that Alice wants to send. In this part, because we need to do many taps before the actual communication, and we only keep the successful part, we call it the distillation. A quick summary. In real-time communications, if there are too many errors, then the decoder will fail. Because of this, we first use error correction before the actual communications to improve the purity of Bell state. And then, for the real-time communications, we use this good Bell state to do teleportation of the actual data. Now, for our third poll question, what is the primary purpose of quantum distillation? Okay, the answer is C. The goal for distillation is to improve the purity of quantum state. The rest of them are not the primary purpose. So next, let's go through how to do distillation. Directly creating a Bell pair between Alice and Bob through a noisy quantum channel won't allow Bob to correct errors, leading to failure. Thus, we apply quantum error correction. Starting with a Bell state and stabilizers, after encoding, Alice can get K-coded Bell pairs and signs. Because we use the Bell state here, the encoder could be implemented by stabilizer measurement on Bell state. And then Alice can send the stabilizer generator and signs to Bob through a classical channel. Subsequently, Alice sends part of the coded Bell pair to Bob through a noise quantum channel and keep another one. Upon receiving the other part of the coded Bell pair with errors and stabilizer generator, after a measurement quantum circuit, Bob can get the syndrome of error. Using stabilizer signs and the syndrome for error, after decoding, Bob can get the estimated error. If the estimated error matches the actual one, Bob can correct it using a quantum circuit to get the coded state without error. Finally, they can form a perfectly coded Bell pairs between Alice and Bob. In the end, let us sum it up. First, quantum error correction. That means based on the classical information that include the stabilizers and the sign for stabilizers, plus the quantum states, we can correct the error in the noise quantum channel. Second, teleportation. That means based on the classical information, that includes the difference between the coded state and the coded Bell pair, plus a perfect Bell pair. We can transfer the quantum coded state by using classical information. Third, distillation. That means based on the classical information that includes stabilizers and Sanford stabilizers, plus the unperfect Bell pair, we can correct the error in the noise quantum channel. We can do this one again and again to avoid quantum channel failure. So that concludes our discussion for this part. Okay, so thank you for this one. So any question? Oh,
Thank you, Sijie. You can show the last slide, which has the course survey.
yeah.
Thank you, Michele. Thank you, Sijie, for putting together these nice slides. Hope everyone learned something about classical error correction, quantum error correction, and how to apply them to networks. So I put my email ID in the chat. So if you had any questions later on, feel free to send me an email. I'll try my best to answer your question. So I see one question in the Q&A, which I thought we'll answer live. So what is the advantage of using QEC for distillation, where you need to set the coded qubit to one party and do local measurement? So good question. So we need distillation because the bell pairs we create physically between different pairs of nodes in the network will be quite noisy. So the experimental setup that you have to generate raw bell pairs doesn't give you good fidelity bell pairs. So we need some method to improve the fidelity. So that we agree on. There are techniques to do entanglement purification, so to purify bell pairs without using error correction, but they turn out to be inefficient. So they are simple protocols to implement, but they are quite bad in how many input noisy bell pairs you need to get even one output bell pair. So that conversion rate and other aspects of those kind of purification protocols are quite bad, which is why we turn to error correction. So either way, you need to generate bell pairs between parties and do local operations and classical communication. So that doesn't really change between whether you're using error correction or don't use error correction. But the advantage you get with error correction is that all the good properties of your code. So if you use LDPC codes with optimal parameters, then your conversion rate from bad bell pairs to good bell pairs will be quite high. And all the advantages you get from decoding errors will translate. So that's the main notion. And also you get fault tolerance, meaning that even if your local circuits in the repeaters and in the nodes are noisy or not reliable, then if the implementation of the code is fault tolerant, then your distillation itself will be fault tolerant. And the distilled qubits, the distilled bell pairs, can be stored encoded in the code in the memory of the repeater, and then you can use them only when you want. So there are many advantages that come by using QEC rather than not using QEC. So hopefully that answers the question to some extent. Any other questions? We're almost out of time, I think, but you need additional qubit transmission, which is, yes. That's a good question. So that's what Michele called redundancy. So if you encode k bits into n bits or k qubits into n qubits, you're adding these n minus k things. That's the redundancy. That's the price you pay to be able to correct errors. Now, the advantages you get are you really have to take the fraction k over n and see if you can construct a family of codes with a good rate, a good asymptotic rate, I should say. Their rate will converge to some number if the family is a good family. And you compare that with the error correction properties of the code. How many errors the code can correct given a specific decoder, and whether the decoder is practical, fast, efficient. So it's really a trade-off. And there are ways to measure the trade-off, compare different coded schemes. And that's the whole area of both classical and quantum error correction. Sure, you can do quantum communication from Alice to Bob without using entangled pairs, which means you're taking the risk of doing real-time quantum communications, meaning you have to send quantum data live. And if something happens, you rely on your decoder to fix things. But that's the issue that Sijie raised, that instead of doing real-time quantum data transmission, if you have pre-shared bell pairs, and you can purify them as much as you want. They are independent of your data. And whenever your fidelity is good enough, then you can use teleportation to communicate your data. And that's a more reliable and standard way to do things. But I think the word is still out on in what settings you should do direct communications versus use bell pairs. I don't quite know what you mean by paradigms of QEC. So quantum error correction, as you see, is a mathematical field that has these error correction methods. Now you can use it for fault-tolerant quantum computing. You can use it for quantum networking, like Sijie explained. You can use it in quantum sensing. So yeah, whenever you have some application that uses quantum information to do something, you can suitably design quantum error correction schemes if you know something about the noise mechanisms in that application. Oh, non-stabilizer codes. Okay. Right. So stabilizer codes are the most often used codes simply because they are the quantum versions of classical parity check codes, kind of classical linear codes. So which means you can construct, efficient codes, efficient decoders, and things work great. There are non-stabilizer codes in the literature called, say, subsystem codes, for example. It's actually a generalization of stabilizer codes. So subsystem codes is something you might want to look at. There are also other codes which are really not stabilizer codes. So for example, one is, let me just type it as an answer. It's called code word stabilized quantum codes. So those are non-stabilizer codes, but they have really not taken off because you don't get a lot of these convenient properties that you get with stabilizer codes. That's the primary reason we use stabilizer codes. And that's also the reason why we use linear codes classically. Great questions, great questions. Oh, particular families of codes. Yeah. So there are these recent LDPC codes that I flashed in one slide. Yeah, so the hypergraph product construction, and then the extension of it, the lifted product construction, the quantum Tanner codes. I think those are the exciting code families that people are looking at. But they're also, kind of challenging to implement in hardware. So, I think there's a lot of work to be done. There's a lot of scope for work. Trade-off in communication setup is beyond simply the coded because okay, we can be lost in which case you can initiate decoding. Yeah, so good question. So if you lose qubits, depending on how you physically make the qubits, we talked about errors, but there are also this concept of erasures. So erasures are when you lose a qubit, or classically you lose a bit, meaning you have no clue about what data it had. Classically, you don't know if it's a 0 or 1. In quantum, you don't know what quantum state that was. So there are erasure decoders. So one way to do it is at the receiver, if you know which qubit you lost, you can reinitialize a raw qubit and then entangle them with the remaining qubits by measuring the stabilizers again. And then that'll give you a new syndrome. And then you can run a decoder to correct that syndrome. And you hope that the erasure is corrected properly. So I'm kind of being hand wavy, but that's the idea. If you know which qubit you lost, that's an erasure. And then there are ways to decode erasures. So yeah, so the trade-off is indeed beyond simply the code rate. You have to consider a lot of factors given what practical setup you have.